So one way to represent the same diagram that we have presented in the last slide is something like this. So you typically have a loop, and basically this loop will be running n number of tx time, the number of sequence that you have, and that is also typically used in RNN neural network. But it's essentially the unfolded version that you saw in the previous slide is represented also in a smaller or succinct way using the diagram that you see right now. Okay, so again, this is essentially equivalent to what you have is A0, and then x1, which is input to this, and then you have output that is going to there. So this, we are unfolding this for tx time. So this is what we are going to be doing. We are going to be essentially increasing the number of layers depending upon the problems that we have, and we might have maximum number of things, right? And again, today we are not going to be discussing the cases where how to take into account like the different number of inputs and output, but all the RNNs are equipped well to handle those cases. Okay, so one thing that I want to emphasize here, why this, you can see that we have multiple different layers now, right? So you may be thinking that since we have this many layers, and now these layers depend upon the amount of words we might have in the overall sequence, or this tx, which is like 9 for the example problem that we are running, but this might be 20 if the maximum number of words in our repository of a data set is 20, then this will lead to 20 layers. So this will be a very deep neural network, because for each of these hidden layers we need to have our own parameter. It turns out that's not the case. The weights that we use for the activation input, for the representing the the linear combination of weights to the x that we have, and the output, there are 3 weights which is denoted by WAA, WAX, and WY. They remain the same for all the different layers. So we do not have specific layer specific weights, unlike in DNN where each layer has its own weight. What we do is here we keep the weights, these 3 categories of weight, constant throughout this overall sequence that we have. What we do is we have an intelligent way of processing the same way and taking into account the sequences. So the WAA is going to change from one sequence to another and going on, but essentially the number of parameters that will be required to train this neural network will be only dependent upon the WAX, WAA, WYA, and that is something that you can define, and that will be fixed for this overall architecture. So we do not need these 20 layers or 20 different weights. We need only 3 weight matrices that sequentially we will process in order to get this overall architecture that we have. Okay, so that is something to take a note of it. Okay, so now let's move on, and again, so here is one important thing that I want to mention. The important aspect that you want to recall from this is, let's say if I want to focus on output y cap 3, the calculation of the y cap 3 is dependent upon not only x3, but it is also dependent upon the previous words x1 and x2, and they are linked through these computations of activation A and activation 2. So again, when we provide this input, these 3 things essentially affects the overall calculation for y3. So not only the third word, but the second word and the first word also affects what should be the output that is going to be given. And this allows us to take into account the context or the sequence information to predict what is going to be happening there. So right, so depending upon what words are here and what word is here, they all will dictate whether the output in the name identification is going to be 0 or 1, because this will give us the context whether this word is a name or not. And this is something fundamentally different than all the deep neural network or CNN architecture that we have been talking, which does not take into account the previous sequence to predict what is happening in the overall problem that we have. Okay. So with that, I think I want to at a very high level cover the main computational aspects of an RNN neural networks. So what are the things that we need? As I said, even though we have these 20 things, there are sequence of 20 things, but essentially the parameters that we need are WAA, WAX, and WYA, and that's constant for the overall. We will do multiple sequence processing for those values, but the number of parameters are way smaller than the number of layers that you see represented in this overall diagram. So this whole block, the first block, could be taken, and this A0, A1, X1 and Y1, the computation could be represented with what you are seeing here in this overall block. So you can see that there is an activation coming from the previous layer, and there is an input in the current layer, and then what you do is you do some bunch of computations. What are the parameters? WAA. Now we have AT minus 1, which is like the activation coming. So what we do is we take this activation, we do the linear sum of that activation, and that's the linear sum here. And this is something that we are doing also in the deep neural networks. Here we have input, the linear combination of input is that is there. We add this linear combination of input with the linear combination of activation by including a bias term, okay? And then we pass on to a non-linear activation function, which is tanh. Right? So it's exactly similar to the deep neural networks where we had some linear combination of input plus bias, but the one term that is being added now here, which is slightly different than deep neural network, is that we are also doing the linear combination of weights with the activation. And then once we get this, we are passing that to a non-linear function tanh. Okay, so that's the only difference is like you have this one and this one in the deep neural network, but now since you have also taken the activation from the previous layer, you need to sum that up, and that is included in this overall computation. And then the Y output is essentially, taking the, whatever you have computed, the YA activation T, you multiply that with the linear combination, okay, add a bias, and then pass it through a softmax layer that could be used to classifications. Okay. So this is what you will use as a computational block to compute the input to output mapping for each blocks and there might be, essentially, as you will see, there might be, 20 different blocks that you have. For 20 different, is the maximum number of words that you have in a sequence is equal to 20. So you have this softmax, and you have this all this, and you essentially have this 20 different blocks. So what you do, you take X input, A0 as an input, and then using this computation, you predict Y1 cap, and also you have an activation A1 that is passed on to the next layer, which is taking that as an input, and X2 as an input, it is doing Y2 as an output, and then giving you A2 output, which is going to the next layer. So this kind of computation, when you're doing this in a sequence form, you are essentially carrying out the first step of any neural network architecture, which is known as the forward pass. Now, once you have done the forward pass, what you can do is you can also do the second step, which is known as the backward pass, right? So that's the second main step of any neural network architecture. And what you need to do in that is basically with respect to the objective function, the cost function that you define, you need to compute the gradient of the cost function with respect to the parameters that you might have. And we have three set of parameters, like we have WAX, WA, and WAY. So we need to take the loss function, and we need to take the essentially the derivative of that, and that is also done in the backward pass. Now the backward pass also passes through all the multiple blocks that we have, and here are the equations that I've written, and I will not go through much details about this equation, but essentially these are the equations that you can derive using the tanh and the softmax function that I have been talking about. Right. So this will give you the set of equations that you can use in the backward pass step to do the backward pass. And once you get the backward pass, the third step, which is always the parameter update step, that will be done through the gradient descent algorithm, and you will basically updating the weight parameters, using some learning parameter that you might have. And this is very, very similar to what you have in deep neural network or in the CNN and so on. These three steps are not going to change, only the equations are slightly changing with respect to the RNN architectures that we have. Now, so what we talked about right now is what is known as the basic RNN architecture, or basic recurrent neural network architecture, which is also known as vanilla recurrent neural network. Now this has some challenges. Even though it is able to process sequences, one of the potential challenges this classical recurrent neural network model has, it suffers from what is known as vanishing gradient or exploding gradient issue. And what happens is, like, since you have multiple different blocks where the computations are passing from one block to other block and then back propagating from one block to another block in a sequence, you might encounter this issue where you're multiplying different matrices from block to block to block. And if the matrices values are small, this multiplication of multiple small values in a sequence can lead to smaller values. And this is then, in many cases, when we are doing the back propagation step, those computations, the gradients that we will have, are going to be diminishing and be becoming smaller and smaller. And so that is known as vanishing gradient. Or in some cases, if the entries of the the matrices are high values, and since you're doing multiple different multiplication in the sequence, we might be doing multiplying bigger numbers, and it might be exploding gradient. And this essentially causes problem in the overall learning of the recurrent neural network architecture that we have. And in many cases, this does not allow a basic recurrent neural network to learn good from the set of data. And it's very hard to train a classical recurrent neural network that gives you a very good results. And so in order to deal with this issue, there has been some other variations in the recurrent neural network that has been developed, which are basically nowadays used in a lot of different problems that we have. For example, there is known as LSTM, long-term short-term memory architecture. There is something called GRU, gated recurrent units. And these are some modification of the basic architecture with additional computational steps that takes care of this issue of vanishing gradient or exploding gradient that we have. And they basically are more effective way to implement the recurrent neural network that you have, and they leads to really good results. And in that case, you typically do not suffer the vanishing gradient or exploding gradient issues that is out there. Now, discussing those within 1.5 hour time is a difficult issue, so we'll skip that. But essentially the basic nature of them is very, very similar to recurrent neural network. What is essentially changing in that setting is the computational block that you have here. This computational block has some other additional computation that goes on. So you basically have some more these blocks from one block to another that is taken into account to address several of the shortcomings that is there in the classical. So the basic, everything except the sequence, the representation, nothing changes. What changes is essentially what is there inside this computational black box. This computational inside thing, the input AT, XT, YT are very, very, very similar. But what changes is inside here, and sometimes you add some more component which is passing on from input to output and so on, right? And that allows you to handle for the issue of vanishing gradient or exploding gradient, and that gives you recurrent neural networks which are more stable, which are more accurate than a classical neural network like a vanilla neural networks that we have. Okay. So again, I will encourage you to look into LSTM and GRU type of architectures.